was a commercial flight, Malaysia Airlines. It was a routine procedure, a routine flight, as we say.
How can you lose a jetliner? How can it vanish in thin air?
That the signal disappeared, that was the unusual element, which was chirping
There
back.
is a specific kind of silence that follows a disaster when no one can explain what happened. It is heavier than ordinary silence. It presses down on families, on governments, on engineers, on investigators, and it refuses to lift until an answer arrives. For the families of the 239 people aboard Malaysia Airlines flight MH370, that silence began on the morning of March 8, 2014, and it has barely broken in more than a decade. But in the last 2 years, something has shifted. Scientists have pulled evidence from the most unexpected places. They have read the chemistry locked inside the shells of sea creatures. They have gone back through a decade-old database of amateur radio signals and found a ghost trail in the sky. They have sent robotic submarines 4 miles below the surface of the Indian Ocean. And while the plane itself still has not been found, what researchers have uncovered has fundamentally rewritten what the world thought it knew about where to look and why the original search was wrong from the very beginning. To understand why this matters, you have to go back to that night. Malaysia Airlines flight MH370 was a scheduled flight in the early morning hours of March 8, 2014, from Kuala Lumpur, Malaysia to Beijing, China. It was a routine red-eye, the kind of flight that thousands of people take every year without giving it a second thought. There were families traveling, business passengers, tourists. Captain Zahari Ahmad Shah, a highly experienced pilot with over 18,000 hours of flight time, was in command. The plane was a Boeing 777, one of the most reliable commercial aircraft ever built. There was nothing on that departure that suggested anything unusual was about to happen. Wikipedia. At 1:19 in the morning, Captain Zahari made routine radio contact with air traffic control. He said good night in the standard manner and handed the communication over to the next sector. Then, almost immediately, the plane disappeared from civilian radar. What made this different from an ordinary radar dropout was what happened next. The transponder, the device that announces the aircraft's position to the outside world, had been manually switched off. Military radar in Malaysia caught the plane making a sharp, deliberate turn, swinging back across the Malaysian peninsula and heading northwest out over the Strait of Malacca. This was not a drift, not a mechanical glitch. Someone in that cockpit had made a decision. The plane did not crash. It kept flying. For several days, search teams concentrated on the South China Sea, the place where the signal had gone dark. It was a catastrophic error that consumed weeks of precious time. The plane had gone in the opposite direction entirely. While ships dragged the wrong patch of ocean, a small piece of science was quietly preserving the truth. The Boeing 777 was still communicating in a limited way, not with air traffic controllers, but with a satellite. Once an hour, the aircraft and the Inmarsat 3F1 satellite exchanged what engineers call a handshake, a basic electronic check-in that neither side could manually disable. These pings recorded the distance between the plane and the satellite at each hourly interval, producing a series of 7 concentric arcs across the globe. Each arc showed where the plane had been during each check-in. The 7th and final arc, logged at 8:19 in the morning, looked different from all the others. The signal suggested the aircraft's engines had failed. The plane had run out of fuel somewhere along that final arc, a massive curve crossing the remote southern Indian Ocean. This was the foundation on which the entire search was built. Australian authorities used the satellite data to construct what they called heat maps, probability charts showing where the debris was most likely to have sunk. They focused their efforts on a lengthy stretch of the 7th arc between roughly 36 and 40 degrees south latitude. For years, nothing was found. Then, in July 2015, a beachcomber on Reunion Island, a small French island off the coast of Madagascar, found a 2-meter piece of white metal among the volcanic rocks. It was a flaperon, a movable control surface from the wing of a commercial aircraft. Serial number checks against Boeing's records confirmed it without question. This was the first physical proof that MH370 had ended its journey in the Indian Ocean. For the families of those aboard, it was a moment of terrible, necessary truth. But attached to that flaperon was something investigators barely noticed at the time. The metal was blanketed in thousands of small, stalked crustaceans, gooseneck barnacles, the species known scientifically as Lepus annitifera. A team led by researchers at the University of South Florida developed a forensic approach using stable oxygen isotopes recorded in the shells of gooseneck barnacles attached to the flapron. The science behind this is called sclerochronology, and it works on the same principle as reading the rings. Inside a tree trunk, barnacles build their hard outer shells one microscopic layer at a time, using calcium and trace minerals from whatever water surrounds them. Every layer records the chemical signature of the ocean at that precise moment. The ratio of oxygen, 18 isotopes within each layer, shifts depending on water temperature. Cold water produces a different chemical signature than warm water. This means the entire history of a barnacle's life, the temperatures it encountered, the currents it passed through, the months it drifted, is preserved in its shell like a tiny chemical diary. Science Daily. The researchers performed careful laboratory calibration to determine how this barnacle species records temperature in its shell, and used the oxygen isotope data along with a growth model to reconstruct a temperature-time history of the flapron's journey. They then compared this reconstructed history against 50,000 computer-simulated drift paths generated by releasing virtual particles into ocean reconstructions from 2014 and 2015. Letting the currents carry them and recording where they ended up and what temperatures they encountered. The barnacle data could then be matched against these simulated paths to identify which ones were chemically consistent with what the shells had actually recorded. EOS. What the analysis revealed was striking and deeply inconvenient for the official search. The temperatures recorded by the barnacles in their earliest shell layers did not match the water temperatures in the original search zone. The chemical signatures in the innermost oldest layers, the ones formed closest to the moment of impact, pointed to water that was significantly warmer than the cold southern stretches of the Indian Ocean, where searchers had concentrated their attention for years. The barnacles were not lying. They had been growing since the moment the flapron hit the water, and their very first layers had been formed in a different part of the ocean entirely. The data pointed further north toward warmer waters, suggesting the plane had gone down in a location that the original 2014 search maps had simply not covered. Indian Defense Review. According to the lead researchers, analyzing larger and older barnacles from other pieces of debris could potentially allow scientists to reconstruct a more complete drift path toward the impact site, since current studies have produced only partial reconstructions due to the small size of available specimens. This is not the end of the barnacle story. It is the beginning of a new chapter. Every piece of MH370 debris that washes ashore could carry with it another biological recorder, another archive of temperatures, another set of coordinates pointing backward through time to the place where the plane first struck the water. And while marine biologists were reading barnacle shells, a retired aerospace engineer named Richard Godfrey was doing something entirely different. He was looking at radio signals. Godfrey identified disturbances in a global amateur radio network called WSPR, Weak Signal Propagation Reporter, which has been operating since 2008 as a way for amateur radio enthusiasts to bounce low-power test signals off the atmosphere to measure signal propagation. What Godfrey realized was that a large aircraft like a Boeing 777 passing through one of these radio beams would create a tiny but detectable disturbance, a ripple in the signal, similar to the way a car passing through a laser alarm system triggers a sensor. Because every WSPR transmission is automatically logged in a massive public database with precise time stamps, Godfrey theorized that the night of March 8, 2014, should contain a trail of disturbances in that database corresponding to the path of MH370. BBC Science Focus. By analyzing the data and working from a known radar position, Godfrey's case study presents dozens of positions for MH370 over more than 6 hours of flight, as detected through anomalous WSPR signal links. The path he reconstructed matched the satellite ping arcs with remarkable consistency. It also revealed details the satellite data alone could never provide, including what appeared to be a holding pattern off the coast of Sumatra, a period during which the aircraft seemed to fly in a wide circle before finally committing to a southward heading. A holding pattern is not a mechanical event. It implies deliberation. Someone was managing that flight. The WSPR analysis suggested the plane was under human control for much longer than many investigators had believed. MH370 search. In a 2024 analysis, Godfrey noted that the flight path recovered from Captain Zahari Shah's home flight simulator passes directly through the WSPR-defined crash location. a convergence he described as not coincidental. The FBI had previously recovered deleted data from a simulator Zahari had built in his home. That data contained a flight session in which a virtual Boeing 777 flew south over the Indian Ocean until the fuel ran out in a desolate, unpopulated stretch of water. The similarity between that simulated route and the actual flight path of MH370 was chilling, and the whisper analysis only deepened that unsettling symmetry. MH370 search. Not everyone agrees that whisper data is reliable enough to use as forensic evidence. Researchers at the University of Liverpool have been conducting statistical tests on known Boeing 777 flights with confirmed trajectories to determine whether whisper anomalies genuinely correlate with aircraft positions, and they are working to validate whether Godfrey's hypothesis holds up at scale. The scientific debate is legitimate and ongoing, but the fact that two entirely independent lines of evidence, barnacle chemistry and radio signal analysis, converge on a similar region of the southern Indian Ocean has given investigators confidence that the search area has been meaningfully refined compared to what was believed in 2014. BBC Science Focus. That confidence was enough to send ships back into the water. In March 2025, Malaysia signed a no-find, no-fee agreement with the marine robotics company Ocean Infinity, which pledged to search a 15,000 square kilometer area of the southern Indian Ocean. If the company found the wreckage, they would receive up to $70 million. If they came up empty, they would receive nothing. Ocean Infinity deployed its Armada vessel equipped with a swarm of autonomous underwater drones, known as AUVs, capable of diving nearly 4 miles below the surface. These robots swept the seafloor using high-resolution sonar, mapping every ridge and canyon in a region of notoriously rugged underwater terrain. Wikipedia. The primary search target during the 2025 and early 2026 operations was an area recommended by retired Air France pilot Patrick Blely and Belgian investigator Jean-Luc Marchand, centered around 35.7 degrees south, 93 degrees east, a zone that had not previously been searched. The search was conducted in multiple phases, with the vessel returning to port for resupply between operations. On January 23, 2026, Ocean Infinity departed the search area after spending a cumulative total of 151 days at sea since 2018, mapping more than 140,000 square kilometers of seafloor across all its MH370 operations combined. The wreckage was not found. Changing TMS Ocean Infinity. On March 8, 2026, the 12th anniversary of the disappearance, the Malaysian government released an official statement acknowledging the search had not yielded findings that confirmed the location of the aircraft wreckage. Ocean Infinity stated that the end of this phase did not represent the end of its commitment to finding the plane. The seafloor in the southern Indian Ocean is not the flat, featureless plain that early search planners imagined. It is home to a massive underwater mountain range called the Broken Ridge, a landscape of jagged cliffs, deep canyons, and narrow crevices where a plane the size of a Boeing 777 could rest completely invisible to sonar passing overhead. The technology is extraordinary, but the terrain is more challenging than almost any other place on Earth. Investigators believe they may be within hundreds of meters of the wreckage, a heartbreaking distance in an ocean this vast and this deep. AOL. Meanwhile, the science has not stalled. A December 2024 paper in the Journal of Navigation by retired University of Tasmania scientist Vincent Line argued that MH370's final 2 satellite signals are more consistent with a controlled, eastward descent rather than the long-standing interpretation that the aircraft entered a rapid, uncontrolled dive after running out of fuel. If Line is right, the impact zone could be different again, and the investigation would need to reconsider once more where the plane entered the water. The mystery has a habit of producing new evidence precisely when it seems like all avenues have been exhausted. AOL. What this decade of searching has produced is not just frustration. It has produced a revolution in how we look for things lost in the ocean. The Barnacle research published in the journal AGU Advances in 2023 established an entirely new forensic discipline, using stable isotope sclerochronology on debris-attached marine organisms to reconstruct drift paths. It is a methodology that did not exist before MH370, and it will be available for every future search involving maritime debris. The Whisper radio tracking analysis has similarly opened new possibilities for passive radar surveillance, using data that already exists in public databases and requires no new infrastructure. Because of MH370, aircraft tracking rules have also been changed globally,